We're going to start our last topic in quantum mechanics now with the quantum harmonic oscillator. The harmonic oscillator is something we've certainly seen in classical physics. It's the potential that's associated with a Hooke's law type force. F is minus kx, or for the potential, U is 1/2 kx squared. K is the so-called spring constant, and describes a potential that looks something like this. It's a parabola. And the potential diverges to infinity as x goes larger and larger. So it's a potential that keeps the particle confined to a small location around the origin. This turns out to be an extremely good model for many applications in physics where one is trying to describe a bound system. And there are actually many harmonic oscillator situations, as we'll review in a separate video. Classically, if the particle has energy E, one expects the particle to turn around at 2 points here. Plus and minus x naught. This occurs whenever E equals the potential energy. At that point, the particle is not allowed to go any further. So at these two locations, these classical turning points are square root of 2 times E over the spring constant K. You might also remember that the potential can be written as 1/2 omega naught squared, where omega naught is the anchor frequency associated with this oscillator, in which case this expression is written as 2e over m omega naught squared. We've already graphed, actually, these wave functions for the harmonic oscillator in the past, and they have a relatively simple form. We'll expect beyond the classical turning points here that the wave function should damp off in some fashion, and depending on which energy level we're talking about, the wave function should have the usual form. So for the first ground state wave function, that might be a sketch of the wave function. The second one should have a node somewhere in the middle. Actually, by symmetry, it should be exactly at the middle. And then 2 antinodes. So I again expect the second one to penetrate out and beyond the classical region, but to do so further because its energy will be higher. And this will be an odd state. As opposed to psi 1, which was an even state. Sure, I haven't drawn that exactly symmetric. Psi 3 would go back to being an even state again, and would penetrate even further into the classical region. So qualitatively, it might look like something like that. I'm sure I haven't drawn this exactly right. So we expect some sort of damping off to the sides over here. And we expect the usual number of nodes and antinodes in the center. I will say that there's something unusual about this set of nodes and antinodes here, and that is that since the potential is constantly changing, the amplitude should constantly be changing of this thing, and the wavelength should be constantly changing. Remember that inside the kinetic energy, which is always the energy minus the potential, equals h bar squared k squared over 2m. Low k here, I guess I shouldn't write low k here, put 2 pi over lambda. That's a little confusing. We have too many k's now. This is not the same k as in the Hooke's law of force. This thing that's related to the wavelength is constantly changing because the potential energy is changing. So these things that look like sinusoids inside the potential here can't exactly be sinusoids because the wavelength is changing throughout this potential. So that's one important thing to think about with this particular potential function.